This recording is to cover the section on life tables. It's actually several sections. And a life table is just another way to represent a survival model where the survival distribution function values are shown at some integral time values. In this case, the example is of a human population, and the time values are years. Now in this table we see that the oldest age you could live to is 109, and you would not live to 110, so the lifespan in our table is 110. We can answer some basic survival distribution probability questions. The probability of a newborn surviving to age 3, that's just S03, and we can read that right off the table, 0.97160. The probability a newborn dies prior to age 2 would be 1 minus the probability a newborn survives to age 2. And that would be 1 minus 0.97259, which is 0.02741. We can answer many other probability questions with the life table involving integral ages. We'll see that in a few minutes. First, let's look at rewriting the life table by adding a new column, the number of lives column, or number surviving to age x, which we will denote by L sub x. It's really an expected value. We're taking a cohort or a radix. In this case, we're going to let the radix be 100,000, and this is just the assumed number of newborns born at the same time, multiplied by the survival distribution function for that cohort. So initially we start out at 100,000. If we multiply 100,000 times 0.97404, then that will be the expected number of newborns to survive to the first year, and that is L1. The expected number of newborns to survive to their second birthday is L2, 97,259. So we just multiply each probability by the radix, L0. From this we get some new life functions that we like to use in discussing the life table. The first is the number of deaths, D sub x. So the number of D sub x is the number age x dying before age x plus 1. And if we extend this notation by putting an n to the left of the d and subscripted, we would say dxn, and that's going to be the number age x dying before age x plus n. Notice it's the difference in the number living at age x minus the number living at age x plus n. And we can then rewrite our p's and q's in terms of these new life functions. So q sub x, of course, is a probability of x dying within the next year. That would be the number dying within the next year divided by the number alive who are currently age x. So this is just a relative frequency probability, and that's what these ratios are. We can then write this just in terms of L's. The number dying, the number age x dying within the next year is Lx minus Lx plus 1. And so we could just write the Qx, probability of x dying within the next year, just in terms of Lx's. Now, Qxn, as you recall, is a number currently age x dying within the next n years. So we could use our D notation. That's the number currently age x dying within the next n years, and we just divide by Lx to get the relative frequency probability. Again, we could rewrite this in terms of my life function Lx. The number dying within the next 10 years will be the difference. Number alive right now at age x minus the number alive at age x plus n. and that ratio would be my QXN. You can also write our P's in terms of LX's. P sub x is the probability x survives 1 year, and so that's just going to be the number alive at age x plus 1 over the number alive at age x. And PXN, the probability age x survives n more years, that would be the number alive at age x plus n divided by the number alive at age x. Likewise, we can come up with the multiplicative rule for the p's if we just write PXN. Just write the definition of Lx plus n. It's just the radix L0 times the survival distribution probability at age x plus n, and the denominator Lx is L0 times the survival distribution function at age x, and the L0's cancel, and we can just rewrite the survival distribution function in terms of the p. And then we multiply by P0x, that P0x plus n is P0x times PXN. And this is our multiplicative rule for the p's. And if we just look at this, we see that age 0 survives to age x plus n exactly when age 0 survives to age x, and then age x survives n more years. So we're just writing down that probability statement, putting a multiplication sign when we use the word and in the multiple events. Now we can define the life expectancy using our life function L sub x. This should be the life expectancy age 0 here, not. So I'm going to put a 0 for the subscript of the E. And the definition is, well, actually, that's the expected value of t0, but we've already shown this integral formula is true. So that's an identity that we already know. And then if we rewrite P0t as LT over L0, then factor out the 1 over L0, we get, in terms of my life function L sub t, the life expectancy. In like manner, we can do the life expectancy for age x. We would denote that this way, and we know already from an identity that this is the integral 0 to omega minus x p x t dt. We integrate the survival distribution function, and if we replace pxt by using the L notation, then that is what? L x plus t over Lx dt. And we could factor out the 1 over Lx. And so that would be the life expectancy for someone currently age x. Now we can use the table to answer some more probability questions, and we're going to write a lot of these in terms of P's and Q's to remind us how to do that, and we need to get used to that. It takes a while to learn to use the P's and Q's to represent probabilities. Now the first one, let's just write in terms of the life functions and do the calculation. So the probability a newborn dies between the ages of 1 and 3. So that would be the number currently age 1 that die in the next 2 years, right, divided by the number of newborns. So the number of 1-year-olds dying before age 3 would be what? L1 minus L3 over L0. And we could read those off of the table. So just reading the L values off of the table, you should get that quotient. And doing the calculation, getting a decimal, you get 0.00244. What's the probability a 1-year-old dies before age 3? Well, the probability a 1-year-old dies before age 3 would be Q12. So Q12 1, 2. Probability a 1-year-old dies within the next 2 years. So that would be 1 minus L3 over L1. That's the formula that we derived. We're just replacing L0 in the denominator above with L1. And so that would be my 97,404 minus 97,160 over 97,404, or 1 minus that ratio, and it's 0.0025. What's the probability that a 2-year-old survives to their next birthday? That would be a P, right? Probability a 2-year-old survives to their next birthday. They have to survive 1 more year. That would be P21. That is going to be what? In terms of the life function, L3 over L2. So we get what? 0.99898. What is the expected number of deaths between the ages of 1 and 3? So, someone currently age 1, the number of deaths dying, those currently age 1 dying in the next 2 years would be the number of deaths between the ages of 1 and 3. So D12 is L1 minus L3. We used that in the above probability calculations already, and if you take that difference, you'll get 244. We want to write as a product of P's and Q's the probability a 50-year-old dies between the ages of 60 and 65. So a 50-year-old dies between the ages of 60 and 65. How can that happen? Well, one way it can happen, or one way to express how that happens, is if you're currently age 50, you live 10 years, but you don't live 15 years. And that way we express it in terms of probabilities. You're age 50, you live 10 years, but you don't live 15 years. So P5010 minus P5015. If you want to express that in terms of dying, we would say that you die before 15 years, but you don't die between 10 years. And in that way, we're expressing it in terms of the Q's. A 50-year-old dies within 15 years, but does not die within 10 years. So 2 different ways of looking at how a 50-year-old dies between the ages of 60 and 65. If we start with the expression in the P's, we can factor the P's. This P5015, we can write P5010, and then if you survive 10 years, you're now age 60, and you need to survive 5 more years, so P65. So we're using the fact that we can factor the P5015 into P5010 times P65. And then we can factor out the P5010 and then 1 minus P65 is of course a Q, Q65. So we can also write the probability a 50-year-old dies between the ages of 60 and 65 as a product of P's and Q's. This skill is very important and very valuable to be able to rewrite the difference of P's in terms of a product of P's and Q's. And we can say what this means. This means this is a multi-event, a multi-stage event where a 50-year-old survives 10 years and then at age 60 does not survive beyond 5 more years. So that's another way, again, of expressing in words how a 50-year-old dies between the ages of 60 and 65, and this would be the way of expressing the probability using those words. Finally, We're going to look at 6.3.3. We introduce a new conditional probability statement and notation that corresponds to it. This notation here, QX in bar M, means the probability that the future lifetime age x is greater than or equal to x plus n and less than or equal to x plus n plus m, given the fact, of course, that a newborn has survived to age x. So this is a conditional probability statement. The probability someone currently age x living in more years but not living n plus m more years. Okay, so the previous problem, we had the 50-year-old dying between the ages of 60 and 65. So that would be 50, Q50, surviving 10 years, but not beyond 5 years. So that's how we would write the previous probability that we just calculated. Or we just wrote them P's and Q's. So let's see. Let's go ahead and let's write this in general here. This is a conditional probability. So the probability age x lives to age x plus n actually I need to kind of, I think I'm going to change this to a newborn.